Welcome back. We will be defining a special set here. So let's let z subscript n uh, be denote the set of positive integers, set of integers from 0 up to n minus 1. Now, where are they coming from? Well, recall that congruence modulo n is an equivalence relation on the set of integers, and these are the distinct classes. These are the distinct equivalence classes which for this equivalence relation, and we also call them residue classes modulo n. And it is customary to skip the square brackets and just write this class representatives. So Zn is this. So here is Zn, and we're going to define addition and multiplication on Zn. So addition and multiplication on Zn are defined modulo n. So what do I mean by that? So let's take an example. Let's take Z12. So Z12 would be the set of integers from 0 up to 11. So 6 and 8, they belong to Z12. And if we add them, we get 2. So how do we get 2? Well, 6 plus 8 is 14, and 14 modulo 12 is 2. So remember, addition is done modulo the modulus, right? So here the modulus is 12, so addition here is done modulo 12. Now, what if I multiply 6 and 8? Well, if I multiply 6 and 8, I get 0. Why? Because 6 times 8 is 48, and 48 mod 12 is 0, because 12 divides 48. Also, 9 belongs to Z12. So what is 9 plus 9? Well, 9 plus 9 is 18, and 18 mod 12 is 6. Okay, I have a typo here. This should be 9 times 9. So 9 times 9 is 81, and 81 mod 12 is 9 again. So you see, 9 times 9 is 9 in this set. Now, so again, you get 81, and then modulo 12, that's 9. So again, I have a typo here. This should be 9 times 9. Here are the addition and multiplication tables for Z6. So Z6 is the set of integers from 0 up to 5. So I have 0 up to 5. So this is the addition table. That is, this table gives you all the different the sums of any pair of these numbers. So here you're adding 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, and so on. So here this shows that 2 plus 3 is 5. This shows 2 plus 5. Notice that 2 plus 5 is 7. 7 mod 6 is 1. Notice that 5 plus 5 is 4. 5 plus 5 is 10. 10 modulo 6 is 4. So this is basically the addition table, so which shows the sum of any pair of the elements of Z6. And this is the multiplication table. So again, let's say I multiply 3 and 4. So here is 4. Here is the column for 4. Here is the row for 3. If I multiply 3 and 4, then I'm getting 0. Why? Because 3 times 4 is 12, and 12 modulo 6 is 0. Let's do another one. Let's say I look at 4 and 2 here. 4 times 2 is 6, and 4 times 2 is 8. 8 modulo 6 is 2. 5 times 5 is 25, but 25 modulo 6 is 1. Okay. Now, by looking at the table, we can recognize a couple of things. Notice that in the first table, any row or any the numbers in any row or any column are distinct. So if you look at this row here, all the numbers are distinct here. If you look at the first column here, all the numbers here are distinct. The second thing to note is that every row has a 0 here. So notice that when I'm adding 2 and 4, I'm getting 0. So that tells you when you add 2 and 4, you get 0. So you can think of 4 as the additive inverse of 2, because when their sum is equal to 0. Now look at 0 here. Look at the 0 here. So notice that 5 and 1 is giving you 0. So the additive inverse of 1 is 5. What else? Okay, 0 here. So notice that 3 and 3. 3 plus 3 is 0. So you can say that the additive inverse of 3 is itself 3. On the other hand, if you look at this table, notice that so the first row has a 1. So this means that 1 times 1 is 1. So the 1 is the multiplicative inverse of 1. And then notice that there is only one other 1 in the table, which is right here. And so that tells you that 5 times 5 is 1. It means that 5 is the multiplicative inverse of 5. So the reason I'm calling 5 to be the multiplicative inverse of 5 is because when you multiply them, you get 1. Notice that 2 doesn't have a multiplicative inverse, meaning that you can't multiply 2 with anything to get 1. And you cannot multiply 3 with anything to get 1. So 1 is the multiplicative identity. Why? Because if you multiply anything with 1, you get the same number. So 1 is the multiplicative inverse because 1 times k is equal to k. Here 0 is the additive identity. 0 is the additive identity because if you add 0 to any of these numbers, you get that number. So 0 plus k is k in this table. 1 is the multiplicative identity again because 1 times k is k for any k in this set. Okay, so that's what we mean by addition and multiplication tables for Z6. And here is an exercise where you have to come up with the addition and the multiplication tables for Z12. Another exercise where you have to write down the addition and multiplication tables for Z2, Z6, Z7, Z8, Z10, Z11, Z17, and then the question number 2 says an element A in Zn is called the additive inverse of B in Zn if A plus B is 0. And you need to find the additive inverse of all the elements of Z12. So generally speaking, if I have A in Zn, then what can I add to A to get 0? Well, notice that n minus A, so B should be n minus A. So if you take B to be n minus A, then you'll see that the sum of A and B would be n, but n is 0 mod n, right? So what can I add to A to get 0? Well, n minus A. So A plus n minus A would be n, which is 0 mod n. So the additive inverse of A is just the modulus minus A. An element A in Zn is a unit or invertible, which means that it has a multiplicative inverse if and only if the GCD of A and n is 1. We know this from the time when we talked about finding the multiplicative inverse of an integer. So if you recall, then we said that an element has a multiplicative inverse modulo n if and only if it is relatively prime to n. So any element in Zn is invertible, or it is a unit if and only if it is relatively prime to n, the modulus n. As a consequence, we see that the number of units or invertible elements of Zn is given by phi of n. Because recall that phi of n is the number of integers between 1 and n that are relatively prime to n. So phi of n is exactly counting how many integers in Zn are relatively prime to n. So that's phi of n is the number of elements of Zn that have multiplicative inverses. Notation for the set of units of Zn. The set of units of Zn will be denoted by Zn star or U of n. And Zn star is the set of all integers that are less than n, set of all positive integers that are less than n and relatively prime with n. So I should be saying positive integers here. So this Zn star is a subset of Zn. And obviously 1 is always in Zn star because the multiplicative inverse of 1 is itself. And Zn star is closed under multiplication. That is the product of any two elements of Zn star is also an element of Zn star. Now I'm not going to justify that. I would like you to figure that out on your own. So again, the claim here is that Zn star is closed under addition, which means that the product of any two elements of Zn star is also an element of Zn star. Okay, so a set of exercises where you have to find the invertible elements of these sets. That is, you have to find Z2 star, Z6 star, and so on. You have to find the inverse of 38 in Z83. And also you have to find the units in ZP, where P is a prime number. Okay, so I'm going to stop here, and in the next video we will be going over 2 more slides and which will have a new definition. So see you then.